All right, so now we're going to talk about their surfaces a little bit more. Mercury and the moon, for that matter, do not generate any internal power of their own at all. Now, you think that probably would be true of pretty much any planet, but actually it turns out that the gas giant planets are still generating some power internally. But I'm talking about Jupiter and Saturn. These terrestrial planets, like Mercury and the Earth, do not generate any power. So what that means is that when we see Mercury in the sky, it's actually a very bright object, but it's just shining by reflected sunlight. It's going to go through phases, just like the phases of Venus that Galileo observed. If you remember when we were talking about historical astronomy, the phases of Venus that Galileo observed were one of the main reasons that he was able to deduce that Venus actually went around the sun, not around the Earth. Well, he wasn't able to see phases of Venus, let's say phases of Mercury, because his little telescope was too little to see phases of Mercury. Those are much harder to observe than phases of Venus, but they do actually occur. And because of this idea of having this maximum elongation during the observation, what that means is you're always going to observe Mercury in the first or third quarter. You're never going to see a new Mercury. If you want to see a new Mercury, you're basically going to be looking straight into the sun, so you're going to be blinded. And you're never ever going to see a full Mercury, because Mercury would have been the opposite side of the sun to see a full Mercury, so you can't see that either. So basically, we're always observing Mercury using at either first or third quarter phase. So just as indicated here, we're basically only going to see it at, these are actual photos that are taken in different phases. We're not ever going to actually be able to see a full phase or a new phase. Oh, this is just a nice shot. We have the moon, the sun is about to rise down there, and we have Venus, Mars, Jupiter, Mercury. I actually kind of like this photo, simply because it's sort of a little bit misleading, because you see Jupiter and Mercury seemingly near each other over there, right? I mean, they're actually close to each other in the sky from our point of view, but of course Jupiter is way in the outer solar system, like about 4.5 astronomical units out from the sun. Mercury is 0.4 astronomical units from the sun. So the only reason we see them together is just because of the perspective that Jupiter happens to be in the same direction, but vastly farther away in the outer solar system. So even though they look close, they're of course not near each other. Likewise the case with Venus and Mars, for that matter. And you do get one accurate impression here, though, which is that Mercury is closer to the sun than Venus is. That's really, kind of an accurate thing. There's no trick to that, not an optical illusion. Because the sun is down here below the horizon, and you can see Mercury quite close to the sun, and Venus a bit farther away. But when we talk about Mars and Jupiter, we're getting into the outer solar system, so it's a little more complicated. Right, so the brightness that we see when we look at Mercury is really kind of surprising, because Mercury's albedo is very low. Its albedo is only 0.1. Likewise for the moon, 0.1. These are grayish bodies. And this albedo is the fraction of incident light that's reflected back into space. They don't act like mirrors, but they do, they do sort of return some of the light to space. But only 10% of it. It's actually 40% for Earth because of the white clouds and the bright oceans and things like that. And it's actually 70% for Venus, because Venus is shrouded in light-colored clouds. But Mercury and the Moon are amongst the lowest, reflectivity objects. So they're basically very, very dark objects. They're almost coal-like dark gray objects. And yet Mercury, nonetheless, even though it has this low albedo, it actually appears very bright. But that's simply because it shines by reflected sunlight and is very close to the sun, right? So you can take an object with a low albedo, and if you put it close enough to a super bright light source like the sun, it's going to reflect a lot of light, just because it's being impinged on by as much light as it's receiving. I like this positive photos from the messenger there. All right, so let me see. Supposed to be able to. I really only selected this for the soundtrack, but anyway. But it's a composite of lots of these messenger images, and I'm taking you into the latter part of it there, so it's going to take too much time. But ultra sharp images, which are telling us a lot of geological processes. Again, notice how amazingly sharp those craters are. These craters are probably on the order of maybe 10 kilometers across. Now, those are 10 kilometers across. Look at the tiny features you're seeing are down to the scale of a few kilometers across or even less. It's by far the highest resolution imagery that we've ever had of the surface of Mercury. And we see, not only clusters of impact craters, but we also see that looks like a piece of gefilte fish to me. Sorry, but it just has that spongy look to it there. Okay, but actually we see a huge diversity of features there. We'll talk about some of those things as we work our way through the chapter here. But again, because of this high resolution stuff, we're able to see things that we could not possibly have ascertained from the Mariner. Okay, so let's talk about the orbit a little bit more. We have the semi-major axis, as I already mentioned, 0.39 astronomical units, and the semi-major axis is half the long distance across the ellipse, and it's also equal to the average distance that the planet is from the sun during its orbit. So if the semi-major axis is 0.39 astronomical units, that means that obviously it's a lot closer here, and it's actually farther away there than the semi-major axis. So it's an intermediate value between the perihelion and aphelion distances. When we go through a discussion of the planets, we're going to always refer back to Kepler's third law, which relates the period to the semi-major axis. So when we look at Mercury, we can easily tell from the orbit, from what we see in the sky, that the actual semi-major axis is 0.39 astronomical units. And if we pop that number in to the right-hand side of Kepler's law, in a form where we've isolated the period, what we obtain is 0.244 Earth years, or about 88 Earth days. So in other words, the year, which the year is what corresponds to that period there, the year on Mercury is about 88 of our Earth days. So we have a ratio of about 4 to 1, the length of Mercury's year compared to our year. Because Mercury is closer to the sun than the Earth is, there's always a possibility of transits, or things that we've already talked about. Transits these days are used to discover planets around other stars because of the little bit of reduction in light output that occurs when a planet moves across the face of its parent star. And we have enough sensitivity these days to actually observe that kind of a drop, which is about 1 part in 10,000 or so, or probably even less than that in the case of Mercury. And transits of Mercury, as seen from the Earth, occur about once every 10 years. So this is just a zoom in on that. And let me see. This is actually a video from 2006. Time-lapse photography. We're moving along by hours here, you can see. But back in 2006, it was a beautiful, very clean transit of Mercury across the sun. Now, the transit is just a perspective effect that we happen to see from the Earth because everything lined up perfectly. But you can also see transits of Mercury from Venus, for instance, or from some arbitrary place that happening in orbit around the sun in a spacecraft, or even from some distant star. You could see a transit like this occur, and you would see a tiny drop in brightness as so if you're running some alien telescope, you would say, hey, wait a second, there's a tiny drop in total brightness because there's a black spot. You couldn't see the black spot, but you could deduce its presence by the tiny drop in output. And you could actually use that to discover Becker if you were actually making observations from another solar system. So the disk Mercury moving along sort of hourly increments there in transit. Again, exactly what we just saw, the 2006 transit. And the transit actually was visible across North America to varying amounts depending on the actual sort of zone where you were when you at that time.